Hello everyone, today we're going to be talking about the physics behind MRIs and a process known as nuclear magnetic resonance. That process, nuclear magnetic resonance, can be explained as follows. Here we have a normal proton, just a normal proton, and as we learned last year, protons have a positive charge. And that positive charge spins on its side, creating like a spin like this, and by the right hand rule we see a spin like this will cause a magnetic dipole moment up in this direction, represented by this arrow. Now there are two types of ways that you can spin. You can either spin up or you can spin down. And spin up is characterized the same as up here with this proton, a magnetic dipole in this direction, and a spin down is just in the opposite direction, facing down. Hence the name spin down, spin up. Now without any external magnetic fields, the energy from a spin up proton will be the same as an energy in a spin down proton. Pretty simple, pretty simple. Here we have a cluster of random protons, just normal protons with no external forces, and they're all going in different directions, different magnetic dipoles. This one's going to the left, this one down, and this one up right here. Okay, so when you exert a B field or a magnetic field, what happens is that these magnetic dipole moments tend to line up, not exactly, but this one down here, instead of being down here like this, will tend to line up with this magnetic field, and because it has a angular momentum, instead of lining up exactly, it precesses around an axis that is parallel to this magnetic field. So this axis being represented by this black dotted line, this green line, this magnetic dipole moment, will rotate along this blue circle like this. The axis will rotate like this around this axis, around this center axis that is in line with the magnetic B field, known as the precession axis. Okay, so here we see a spin-up proton and a spin-down proton, and a spin-up proton will precess as follows, in this direction, just up, and a spin-down proton will precess in this direction. Now, I said earlier that spin-up and spin-down protons have the same amount of energy, but that is before having a magnetic field applied on them. So as you can see here, they have the same amount of energy. Now when this B field is applied, this magnetic field, the spin-up protons will go to a lower energy state, whereas the spin-down protons will go to a higher energy state. Now they go to a higher energy state by the same amount, they gain as much energy as the spin-up protons lose. So this shows the conservation of energy. Spin-down protons will go to a higher energy state because spin-down is a more unstable phase, whereas spin-up protons, the spin-up phase is more stable than it was originally, than it was before precession. Now this phenomenon is known as the Zeeman effect and shows the conservation of energy. Now let's see what happens when we emit a radio frequency or an electromagnetic wave perpendicular to this proton that's precessing. So this proton is precessing at a frequency governed by B0 about this axis, and this frequency is known as the Lamar frequency. And once you emit a wave with the same frequency, it will, in the same way that waves, when two crests hit, because they have the same frequency, their waves will intersect. They will cross the same way that waves hit each other and create a larger amplitude and this is a poorly drawn wave. It should be coming out of the page like this. But once this precession comes to a point here like this, outside towards the camera almost, and this wave is in the same direction, they will cause a higher amplitude. And so instead of being right here, the precession will now flatten out. And now the precession keeps going around. It hits another one of these waves, it flattens out a little bit more, and then it hits another one, and it flattens out a little bit more, and you get a flat wave as a result. Now, this radio frequency wave adds energy to the system that wasn't there before. So as a result, all of these spin-down protons, or all of these spin-up protons rather, will become spin-down protons because they're going from a lower energy state to a higher energy state because of this external energy. And so all these spin-up ones will become spin-down ones. Now, once we remove this radio frequency wave, all these protons will go back to their original position. So that means that all the spin-down ones will go back to spin-up, and all the ones that were more flat, precessing flatter, will go to being less flat. And so this is essentially nuclear magnetic resonance. Now, once it goes back to its original position, once it relaxes from the external energy, it emits an energy in return, known as a photon, Okay, so how does this all relate to MRIs? How do MRIs work? What's the science behind MRIs? Well, it's this. Okay, MRIs measure the concentration of hydrogen in your body. Hydrogen molecules have the highest NMR signal, have the highest nuclear magnetic resonance signal, meaning they most readily observe NMR, this process that we just explained. And so because of this, and because of the fact that our body is in 70% water and very densely populated by hydrogen molecules, it is very easy to measure the amount of hydrogen in the human body using this technique, which is exactly what an MRI does. The MRI machine contains a magnetic coil, multiple even, that create large static magnetic fields. Like earlier, this B field is created by large magnetic coils in the MRI machine. Second, a second set of coils, not the same coils, but a second set of coils can create this radio frequency wave also. So this process is replicated through the MRI machine. Now, once this process is complete and we emit photons in return, the MRI machine can measure the amount of photons being emitted and in turn produces a picture based on how many photons. The more photons, the lighter your picture will appear on the scan. And the less photons, the darker it will appear. So for example, if you have a layer of fat is very watery, very lipid. It's made of lipids and has a lot of hydrogen. So as a result, fat usually turns out white on the MRI scan, whereas bone, which has less water, will be darker. And all of the parts of the body have different concentrations of water and different concentrations of hydrogen, and can be seen through through pictures. And that's how you can see a tumor, which has less or more water, or a cyst, or whatever, from an MRI machine. So that's pretty much how MRIs work.